to CS4510, L15A. The topic is computational complexity. What a mysterious area we are now in. So we recall what we just did. We just spent like, I couldn't tell you how many lectures, 6, like what, L10, L9 to L14, so 5 classes, something like 2.5 weeks, 3 weeks on the field of computability theory, in which we ask questions computability, in which we ask things about possibility, right? Or like, what problems have algorithms at all? And in fact, the last theorem we talked about a relation that is in fact undefinable. You cannot ever, in the formal language, express when a statement is true. So we're talking about extremal and perhaps even philosophical results. And in fact, everything was kind of like proved via diagonalization, and there's deep, intimate notions of how these objects relate to intuitive principles. Then we have complexity theory, computational complexity theory, just shortly complexity theory. In contrast, basically what happened is that computability theory, I mean, we basically figured it all out. Like, there's not really any more interesting problems. Europeans are still doing something over there. Don't really know. But they, like anything that you reasonably could ask with philosophical inquiry is basically a solved problem. And the last thing to really be solved was Hilbert's 10th problem in the 70s. Is there an algorithm given a general Diophantine equation to determine if it has an integer solution? We showed one such polynomial. This was done in the 70s, and after this, a generation of scientists moved on to complexity theory. And complexity theory is not about necessarily does a problem have an algorithm at all, but does a problem have an easy algorithm, an efficient algorithm. So this is about efficiency. Now, you may be hearing that we're moving into a field of complexity theory, and your first instinct may be to kick and scream. We're moving from a field which has deep philosophical inquiry to one that is engineering. You know, I have to increase shareholder value. This sucks. That's what my job today is to convince you. No, complexity theory is not really about designing efficient algorithms. Actually, so there's like 7 different ways you could teach a complexity course. Everyone has their own idea about it. And some people teach it simply to make algorithms faster. They're like, if we can understand limits of algorithms, we can make better algorithms. I don't really care. I care about the computational complexity because there's a characterization that it has with computability theory. If we were to describe computability theory as a movie genre, I would use drama, in the sense that there are lots of interesting questions, and none of them have answers that we like. We know, for example, that there are true and unprovable statements. We know that there are undefinable relations. We know that there are unsolvable problems. And there are statements which are completely independent of set theory, but so you can assume it to be true or false with no contradiction. And these are uncomfortable, and we don't like these at all. These don't make, to some, they still don't make any sense. But they are true, and at least we know that they're true. We know that the halting problem is unsolvable. In contrast, in complexity theory, I would characterize this as a horror, because every problem in complexity theory is essentially a time-bounded version of the problem in computability theory, but the problem is we can't actually prove any of it. As in, like, a generation of computer scientists, the P versus NP problem is now 50 years old, and it really is just a time-bounded version of the problems that we're talking about in computability theory. But the history of complexity theory really is a history of failure. We'll talk about this in a more formal sense, but recall that in computability theory we talked about the recognizable, co-recognizable, and decidable languages, right? This is LTM, this is L star TM, those with half a decider, a semi-decider, and this is the complements of those, right? And the intersection of these 2 classes is just the definition of algorithm, right? Is this coming back to you? It turns out if you took the definition of algorithm, which is a machine that halts on all inputs, and you say, let it halt at all inputs with a polynomial time bound, you get the complexity class P. And then it turns out, and this will be a homework problem eventually when I figure out how to release homework 7, that if you took the recognizable languages, in fact, those are equivalent to NP if you made a polynomial time bound on the verifier. So if recall the 3510 definition of NP is that you have a polynomial time verifier. If you remove the word polynomial time, that's actually just a recognizable languages, which is kind of surprising. You'll figure this out on the homework. So we know that P and NP kind of look like this. And then we also, while we have co-recognizable, we also have co-NP, it turns out. Now, the difference is that we know what the world of computability theory looks like because we know, like, for example, the halting problem goes here. And we know that everything with an algorithm goes here, and the halt complement goes here, and EQTM, and we like know everything about it, even though we know it's not solvable. We at least know it's not solvable. In contrast, this is not an accurate picture because this is a conjecture. This is just a time-bounded version of this picture. There's a few differences, but it is, we don't know. We have no idea. We don't know if P is strictly contained in NP. We don't know if the intersection of co-NP and NP is P. This, we conjecture, is strictly contained in that, this little avocado. We don't know if NP equals co-NP. We have no idea if NP is closed under complement. We do know that LTM is not closed under complement, because remember, if it was closed under complement, then it would just be decidable. We have no idea, but all the analogies are kind of the same, except we can't prove it. We can at least prove this, and it's uncomfortable. We can't actually prove this. So that's kind of the struggle. And not only can we not prove it, we can prove that we can't prove it, right? So historical materialism, whatever. Here's the history of the P versus NP problem. It's a graph I'm going to make up. Let the y-axis indicate how confident that the theoretical computer science community is that we can solve the problem, and let that be time. So around 1971, Cook defines the problem. We'll talk about his work later. But it's pretty obvious, like someone's probably going to figure this out. And he doesn't even define it in modern terms, the term LP, NP, and so on. And then people are like working on it for a little bit, and then this kind of groundbreaking result comes out, which sort of ruins confidence. And that result is what is known as a barrier. A barrier is not anything like an independence result, but it rather says, I don't know how to prove it, P versus NP, but I can prove that you can't prove P versus NP. Now what that means is an entire class of techniques cannot resolve the P versus NP problem. So we can separate, for example, LTM from L star TM by diagonalization, right? We can prove that you cannot separate P from NP by diagonalization. So while diagonalization is a separation technique, right? You can prove A is a strict subset of B by creating an object in B whose whole job is to be different than every object in A. So by doing so, it's just not in A because of this property, and then you just happen to place it in B. So diagonalization was basically every single technique we did in computability theory. We can prove diagonalization cannot be used to separate P from NP. Why that is will be something we'll talk about. But basically what it means is a lot of the classic theorems in complexity theory were first started to being explored using techniques from computability theory like diagonalization. And then it quickly realized, hold on, this doesn't work anymore. And not only does it not work, we can prove it doesn't work. So the history of computational complexity is a history of failure because advancements in the theory are invented simply because something else fails. In some sense, the relativization barrier, which we'll talk about in detail later, proves that like lambdas don't work as well. Like anything that is black box computation, anything that's too generic and too simple, not gonna work. You need something hardcore. So some time passes and people are like, you know what's hardcore? A circuit. So people start looking towards circuit complexity. There's a small area here, for like 3 years, people are convinced the problem is unsolvable. Like in the sense of that it is independent of set theory. Like it is undecidable to prove P versus NP. There's some papers in this area that prove, for example, an algorithm exists that runs at n squared time, but there is no proof it runs at n squared time. And you can prove there's no proof. These results are kind of toys and they're somewhat given up. And people are more convinced that the problem is solvable, it just needs new techniques. So people look to other theorems and they're like, wait a minute, the sum of circuit theory has been developed. Let's go to circuits and look what's going on there. So people start looking to circuits and they were able to find certain problems decidable by circuits. Sorry, this is bothering me. Oh, I'm just gonna close that. They were able to show, actually we can prove with circuits, some lower bounds. By the way, what is the difference between an upper bound and a lower bound, right? We would hope to separate P from NP using something like a lower bound argument, right? So given a problem, we know that there are some lower bounds. Name any problem and any lower bound you know in the problem. This is a huge generic question, so you would think there'd be lots of answers to it. But name any problem and any lower bound on the problem.
Any valid lower bound?
Anyone that you know.
Binary searches, log n.
Correct, but that's the one we do in 3510. There's a second one you may know.
Sorting in array or list.
Yes, so
ON, you're forced to check every single determinant.
in the comparison model, there's an n log n sorting lower bound. So the complexity of a problem can be said to be its greatest lower bound and its least upper bound, right? So if you take all the upper bound arguments, an upper bound argument is simply an algorithm. So for example, we would have an n squared runtime, an algorithm that sorts an n squared. We also have another algorithm that sorts an n log n. We have another algorithm that sorts an n squared, right? Now, how many lower bound arguments are there on sorting? Well, first off, there is an n lower bound because you need to read each element. Through a more non-trivial argument, you need to, you can do this tree of the n factorial permutations, and you can get that there's an n log n lower bound, right? So you take the least upper bound and the greatest lower bound, and if those happen to match, then great, the problem is solved. If not, you know the problem is in between those two, something like this, right? What I'm trying to emphasize, how do you prove an upper bound? I give you a problem, how do you give me a big O of the problem?
You give its worst case.
Yeah, sure. The answer I'm looking for is you just give an algorithm. So like, let's say I'm like sort, and then you just write a code for it. I mean, okay. So giving an upper bound is easy because you just have to show an algorithm solves a problem. How do you show a lower bound? That's very difficult. This is in some sense existentially quantified. This is easy. This is universally quantified. To show an upper bound, you just show one algorithm. To show a lower bound, you have to prove that every algorithm that correctly solves a problem, each of those must take some minimum number of steps. That is very difficult to show, and in fact is basically impossible. In an undergraduate curriculum, you learn two lower bounds. N log n sorting, log n binary search. Technically one more. Most problems have a linear time lower bound because it takes at least that long to read the input. For example, computing the minimum of an array takes at least linear time because you have to look at each element. So that's it. I mean, those are the only three lower bounds. So proving lower bounds has been a complete failure in the sense that we don't even have like a super linear lower bound on problems in NP. For example, we don't even know if SAT can be, if we can prove a lower bound on SAT and n to the 1.00001, okay? We can't even do that. So like the history of complexity theory is like we basically can't do anything. What was I talking about? Yeah, so circuits hardcore because you can make inductive and combinatorial arguments. And we'll talk about that later. This is just kind of setting the tone of things. When you take a circuit and you break it in half, you have two smaller circuits. Use a strong induction lower bound hypothesis on that and you can chain upward. So that's kind of the first arguments that were being made. Circuits, highly combinatorial. So you can use a lot of combinatorics that were being developed, right? The P versus NP problem is unique in that it is a discrete math conjecture, right? All the other unsolved problems, Riemann hypothesis, what have we got? Yang-Mills, Goldbach, these are all kind of like in other fields, but the P versus NP problem is strictly a discrete math question, right? So there's not much discrete math that exists. There's like logic and combinatorics, and that's it. I mean, so we don't really have any theorems to play with. I mean, if you compare that to the great number of theorems that are in functional analysis or something geometry, there's a lot more tools. We don't really have tools. Anyway, combinatorics, people look towards combinatorics and applying combinatorics to circuits. And we say, actually, no, we could probably solve the problem. And then in like, I forgot what year this was, 1981 maybe, Razborov proves that there is no monotone circuit for an NP-complete problem. A monotone circuit is one that does not have NOT gates. And people are excited because this is a super polynomial circuit lower bound. Essentially what people are trying to prove in this era is like, okay, fine, maybe we can't prove something like this. But maybe we can prove that there's no polynomial size circuit for SAT. That's related to no polynomial time algorithm. So people are trying to show that there's no polynomial size circuit. Brasborough proves there's no polynomial size monotone circuit. People are excited. The next thing he proves, if you add NOT gates, the proof provably doesn't work. So it's over. People are still inventing techniques and working in this area. Maybe this should be a smaller bump, right? People are still pretty confident that they will find some way to prove no polynomial size circuit for SAT. Until Brasborough proves in 1995 something called the natural proofs barrier, which is like basically all the techniques that have been developed for the past 15 years fall into this broad class he defines as natural. And then he proves no natural proof can prove P versus NP. So basically, this 15-year span, 1981 to 1995, was full of people who became experts on a single technique known as the method of random restriction. It's a very specific, precise technique. People reformulated in many creative ways, but they were basically not able to apply it to the P versus NP problem. They were able to show trivial problems. For example, the XOR function cannot be done in constant depth. That's like a really stupid lower bound, but that's what it takes to prove something like this. Would you mind going over there and asking them to... Yeah, I got it. Man.
They're enjoying complexity theory a lot.
It's gonna be tough to convince them if that's their only work.
Yeah.
They're only working in that room.
He wasn't even hammering anything, he was banging two rocks together. Anyway, the natural proofs barrier comes out, it's over. All 15 years of expertise gone in an instant. It's useless. They were trying to find the golden goose, they couldn't do anything. So it's gone. What other techniques are there? People realize actually we can do some polynomial interpolation techniques. People try to find they find this technique called arithmetization. And wouldn't you know it, we see the pattern by now. Instead of trying to apply the technique, people rush instead to try to prove the technique won't prove P versus NP. And congrats to them, it does. Aronson and Wigderson in like 2008. So what are we left with? What techniques do we have to solve the P versus NP question? Basically, like maybe two. There's one paper from 2014 that has a technique that provably doesn't go here, here, or here. But it doesn't do anything else. It's not really useful. There's another technique that may not fit into this nice framework. And sometimes there are such barriers that are very specific. For example, there was a paper, 2014 or something, like, you guys remember linear programming? Some of this stuff, right? Somebody proved something like, if you use a linear program to solve this traveling salesman problem, through a geometrical argument, the size of the polytope must be exponential. So that doesn't prove that traveling salesman takes exponential time, but it proves you cannot say that linear programming will help you get a polytime algorithm just by arguing about the size of the search. Something like this. That's a very specific kind of argument. But basically, it seems much easier to prove that other people can't prove the problem than it is to prove the problem. We have overwhelming evidence that P does not equal NP, but every time someone tries to prove it, they're proven that they can't prove it, and then a generation of scientists, have a retrospective on the failure, come up with new techniques that exist simply to escape the past failure, and then are stuck in a different wall, right? Now, this is the history and the development of computational complexity as a research discipline, because it's clearly marked by such large scars. It's like the techniques are developed simply to ask, to try to solve this question, but every time they come close, they never were to begin with. We're in fact farther from solving the question than we were when the problem was first announced. Sometimes you talk to old people and they will tell you a story in the 80s, they're like, yeah, I spent a few weeks trying to solve the problem. And in hindsight, now that we have the problem's only 54 years old, now that we know more about the problem, it's like, it seems so naive and silly. Because of course, they were far farther than they thought, in fact, right? Lower bounds are hard, turns out. So, questions on that? Another thing I want to mention about like why like this is such an interesting field philosophically is like, okay, like one, it's hard to prove, and that by itself probably is interesting to want to try to prove it. But two, it is kind of a more practical question than the decidability, recognizability stuff. LTM is like, does there exist an algorithm at all? But that's not really an efficient question. An efficient algorithm is one that you can basically solve. So if a problem has an algorithm, but the algorithm is not efficient, you might as well not have an algorithm for it. If you cannot solve a problem efficiently, if you can prove like this, the fastest algorithm must solve a small instance after the heat death of the universe, I mean, it might as well be unsolvable. So in some sense, it is just a bounded version of the same question. And in fact, the language, you're not going to believe this, MW1 to the T, M on W halts in T steps. This is clearly a bounded version of the halting problem. It's NP complete. So in fact, you can verify it and do a polynomial time reduction to such a thing. So a bounded version of the halting problem, NP complete. Right, so a bunch of history, lots of stuff. What else? Let's just go into the definitions now. Any questions? Okay, so what we seek to measure resource, but there's a few number of resources that you can do. What are some obvious resources you want to measure about an algorithm?
Time and space complexity.
Yeah, time is the most important one. Space, as in the context of memory used, we'll have one lecture on space complexity. Space is not that interesting because when you finish an algorithm, you always get the space back, but you never get the time back. So if you were to measure the space complexity in the algorithm upon its finishing, upon its completion, every algorithm would have constant space, but everything is free. So we don't, to some spaces, you'll see, we'll have a lecture on it. But it's kind of a different thing. There are also some tricks. For example, you can save space. You can do a reverse time-space trade-off and inverse dynamic programming where you save space by blowing up your time exponentially. So you can use a constant amount less space for exponential time, something like this. Some silly things. Anyway, time is the most valuable resource because we're all going to die and things like this. There's other resources you could measure. Namely, sometimes people concern themselves with joules in terms of like how much electricity is required by this algorithm. But you would think that would be a simple constant multiplier of time, and that's mostly right. There's also things like circuit size, how many gates are needed if it's in the circuit model, what is the depth of the circuit required? Can anyone think of any more? There's two more at least.
Number of operations.
In an arithmetic sense, if we were to do, there's like algebraic computing models and they have like, they only can do like addition and multiplication. You can consider operations, but that actually is proportional to time, as we'll see. This is a harder one to do, but we don't really care. Basically the only one we're gonna care about is time. One more I can think of is the number of random bits required. If you have a randomized algorithm, maybe one algorithm uses more randomness than the other. So how much randomness is required? Sometimes algorithms need more than others. Any others you can think of? Okay, that's most of them, right? Time is the most important one. Now, what is the time of an algorithm? Like, the first instinct is to hook a stopwatch up to a computer and start and stop. But as we immediately see, there are some problems with this. So what we actually measure as time complexity is the number of steps of a computational model. So name for me any computational model. Yes.
Binary search.
No. A name for me, not a program, but a computer.
You mean like a MacBook?
Okay, a MacBook. That's kind of too complicated to analyze. What's a simpler computer?
The brain.
That's way more complex. I guess the answer I'm looking for is a Turing machine.
Oh, okay,
Yeah. So any automaton is some kind of computer, right? Now here's the problem. All the Turing machines are effectively computing the same stuff in the field of computability theory, but we're talking about complexity theory. So there's variants of Turing machines, and are they different is the next question we're going to answer. Because some may be faster than others, right? The first basic model of Turing machine is the one-tape deterministic Turing machine, right? It's got one tape, read, write, move. An extension of this is the K-tape Turing machine. We proved that you could simulate a K-tape Turing machine on a one tape, but we didn't really discuss if there was a simulation cost to this, and it turns out that there is. So we'll come back to that in a second. What other models of computation do we know? Yeah.
NFAs and DFAs.
NFAs and DFAs for reasons. So those are models of computation, but they are weaker. So we don't want to study them.
So we're looking at equivalent to Turing?
Exactly, Turing complete models. People do study the complexity of certain problems as I guess as like DFA size in some sense, right?
PDA?
PDA is also not Turing complete, right? But people do study complexity in a refined way on those things. There's like one paper though. Oh.
Can we add non-determinism?
Yeah, NTMs. So now here's the problem. We want realistic models of computation. The non-deterministic Turing machine is a model of computation. But the question of whether or not it is realistic we'll expand upon later. But for now, it exists, and it will actually be used in the definition of NP. But we don't consider it realistic. So not a good choice for now. There's other models. There's something called the word RAM model. I don't know if we discussed this in class, but the word RAM model is commonly used as the automaton when you formalize an algorithm. And basically, it's like a modern computer. It's hard to explain a little bit. There's some details I don't want to get into. But instead of a Turing machine, which is forced to loop left and right, essentially think of a Turing machine with, instead of symbols it writes, it has a register of, say, 32 or 64 bits, the size of the word. So a 64-bit computer would really have that. And it's allowed to jump, in some sense. It has some basic operations, add, move, mult, condition, whatever, right? All those are basically as close to a modern computer, right? If you have a Boolean stored in a byte, 7 of the bits are unused, right? So it's as if you were moving from an alphabet of this size. Also not a bad model for understanding algorithms. There's one more, quantum stuff. Those exist, quantum computers. Let's not think about it though, but they are there. No one has ever built one, but I mean, we're waiting, so. And some theorems are machine dependent, like which model of computation you choose speeds things up. So sometimes we're concerned with the question of comparing these. Right now we're looking for giving a good definition of efficient algorithm though. So I will direct you to the one-tape and K-tape Turing machines, right? Let's do, I ask you for consider the language of palindromes. Let's even make them even length. Okay. Give me an algorithm that decides palindromes on a one-tape deterministic Turing machine. At a high level, don't give me the state diagram, just describe it to me.
It reads one square, marks it, finds the next, or shifts to the next word.
Which one? What will it shift to? Let's say we start at A, which one should we shift?
To the, I guess to the end.
Yeah. So we're gonna go click, 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 click. Oop, okay. Check if those are equal. And then what should we do?
Go back and check the next tape square.
Click, 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 good. And then what should we do?
Same thing, go all the way back.
Okay. A lot of clicking, a lot of stuff going around. It'll eventually work. There's some conditions. Check that the left and the right are the same, do some marking. This takes how many steps? Like n minus 1-ish. This takes like n minus 2. This takes like n minus 3. Right? So what is the number of steps that this algorithm takes? What is like 1 plus 2 plus 3 plus 4? Anyone remember what that sum is equal to?
N times.
So what is that in big O?
N squared.
Yeah, so this is kind of like an n-squared algorithm, right? By the way, why do we use big O in the theory of algorithms? It's the Turing machine's fault, because you can do, like you don't learn about the Turing machine, of course, in 3510, because it's too complicated, it's a 4510 topic, but the reason you do big O is because it abstracts you away from the computer in some sense. There's all kinds of little constants here that are necessary. And in fact, we have speed-up theorems that basically say, like, suppose instead of the alphabet here being 0, 1, suppose instead you made the alphabet 0, 0, 0, 1, 1, 0, 1, 1, okay? That alphabet choice allows you to read the input twice as fast. So for any constant c, if one algorithm solves a problem in t steps, there is another problem that can solve it in 1 over c t steps for any c. So by a constant, there's an arbitrary speedup you can do by hacking the alphabet. Okay? Now does this actually change the speed of the algorithm? No, and this works for every algorithm. So it doesn't really, it's not really part of the algorithm, it's part of the machine in some sense. So we invented big O simply to hide this stuff from us, because it's ugly, and we don't want to consider these kinds of tricks. We're like, don't do this, you know. Right. So this is, it takes n squared time to do this on a palindrome, to decide palindromes on a 1-tape deterministic Turing machine. What about a 2-tape deterministic Turing machine? So let's give that one. I'll give you the algorithm. So first step we're going to do is we have 2 tapes. There are 2 tape heads that can move independently, right? The second tape is initialized to be blanks. What you're going to do first is copy to second tape the entire input. Okay? Next, what you're going to do is reset one head. And let's reset the bottom head just for fun. So now this head is here, but this head is here, okay? Now what you're going to do is, I don't know what to call it, it's called loop and compare. You're going to have this head move that way, this head move that way, and then they're going to check that they read the same symbol. Right? They both read an A, they both read a B, they both read a C, and so on, right? How long does it take to copy to the second tape?
N.
Yeah. How long does it take to reset one head?
N.
How long does it take to do this loop and compare thing?
N.
Yeah. So this is 3n, which we could say is O of n, right? So this takes O of n time. This takes n squared time. Can you do it any faster than O of n? Why not?
You have to see all the time.
Yeah. So palindromes must take at least this long, right? You have to read the whole input. You can't, unlike, in fact, there's only one algorithm you should know that can be done faster than linear time. What is it?
Binary search.
Binary search. Binary search only works because you're allowed to jump around and you're promised that the input is sorted. If you don't know if the input is sorted or not, you must at least first check this. But because you're promised this, you can do this jump around trick, right? Every other algorithm has to read the whole input. So we know that on the two-tape model that we've solved the problem basically, perfectly. But on the one-tape model, we gave n squared. Can you beat n squared? This is kind of too simple of a solution. Is there a way in the single-tape deterministic Turing machine for you to beat n squared?
No.
Yeah. So it turns out not only probably not, but provably not. You can prove that a one-tape DTM must take n squared steps to decide palindromes. So in fact, you cannot speed up the one-tape algorithm any faster. The proof is from Kolmogorov complexity, turns out. If you could, the computation history of the machine actually gives you a shorter way to encode a string, it turns out. So the same way we proved that A and B was not regular, and the same way we proved there was infinitely many primes. A similar proof exists to show this kind of lower bound, which is kind of very interesting. The theorem is from like the 60s, and there was like a 40-page paper from 1965, and then like in 1980, somebody comes out with like a 9-page paper, something like this. So it's like Kolmogorov complexity can be used to make small proofs of theorems. And in fact, this proof is not too hard. I've given just this problem as a final exam, broken up into several parts. Show this with this, show this with this, show this with this. It's not too difficult, actually. It just takes too long for us to do, so I won't do it. But know that the lower bound argument exists. Either way, we know something now. There is a problem that takes linear time on a two-tape, which includes k-tapes, and takes quadratic time on a one-tape. So we can actually, what this proves is that the k-tape machine is provably faster than the one-tape machine. But it appears to be only faster by a polynomial. So we don't actually know like how much faster that is, right? By the way, if I asked you to do this like in, let's say, pseudocode in Python, give me a high-level algorithm that solves this problem. Yeah.
So you have the input string, you copy it, so now you have two strings, and you reverse one of them, or you just index from the end of it and compare.
Yeah, that would work. In fact, what I could say is for I in 1 to the n, if wi does not equal w, if w of I does not equal w of n minus I, right, that's basically it. It's as if there's two pointers, but you don't have to do any copying. This takes how long in Python? Suppose I finish the code. How long does this take?
A long time.
Yeah.
So pretty much just check every single character once.
Exactly. And then there's a lower bound as well. So we know that in Python you also can't do it faster. So a stronger model can't do this one faster. So the one-tape Turing machine is in fact kind of weak. In fact, on any Turing machine, how long does binary search take?
N squared.
It can be done faster than n squared.
N.
Yes. So although log n time is what a real computer takes for binary search, we say that binary search on a Turing machine takes linear time because you have to go click, 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 click. You can't do this, look at the middle element and then jump on the left or the right, because you have to click, 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 click all the way to the middle first, and that takes n squared, n steps, n over 2 steps, right? So immediately, you can't do this faster. So the Turing machine is not maybe the best use of an algorithm, but it's okay because it's simple, and it's more formal than if we were to do, start with a laptop or something. So as a model of computation, it's simple enough that we can argue about it, even though there are some drawbacks. That's the sort of the moral here. Yes?
You said you can find the middle using a normal Turing machine
In linear,
in linear time?
Yes.
How do you do it?
Okay, well, hold on.
You can't keep track of index, right? So you have to go
In the
forward,
one-tape model, maybe
forward.
not.
Right, you have to do it in square,
Yeah.
and that's no good.
Maybe I'll update myself to say it takes at least linear time.
Okay.
In a two-tape, what I could imagine is one tape loops over the input. The second tape increments a counter in some way. And then from there, maybe you can do, you can compute n, you can arithmetically compute n over 2, and then find that index.
But that's a log n, right? Because you need the log n counter.
But it may be able to be done. No, you're right.
It's nasty, this is.
That's an interesting question. I'll amend my statement to say that binary search takes at least linear time on any Turing machine. But the one tape, I don't know how long that should take. There's a lot of creative things you could do with binary search as well, so I'll have to think about that one. Okay, of course, so we have this problem, there are different machines, they have different runtimes. That's kind of annoying. It's not really a problem necessarily. Let time of f of n be the class of languages basically decidable in f of n steps. So we would say that w is in L, which is in time of f of n, if and only if m on w halts, accepts in O of f of n steps. And w is not in L, if and only if m on w halts, rejects in O of f of n steps. So the definition of algorithm, of course, is one that must halt on all inputs. We're not going to concern ourselves with machines that are stuck in a loop at all. Just forget it. But we will concern ourselves with the question of like, does the machine, consider only the machines that halt in a certain number of steps, right? The definition of P is algorithms, is problems, that have polynomial time algorithms. This may be obvious to you, right? By the way, time f of n closed under complement, yes or no? For any f of n.
Yes.
Why?
Because otherwise it wouldn't be decidable.
Yeah, I suppose. Like, the answer I'm looking for though is like if you have an algorithm that runs in f of n steps that it says yes and no correctly, it also says no and yes correctly. If you control f, return true for return false, right? So because it halts on both of these steps, it must be closed under complement. Similarly, P is closed under complement. If you have a polynomial time algorithm to say something, you have a polynomial time algorithm to say the opposite, right? P is an interesting and robust class. And the reason we care about P, before I get into that, by the way, the big O property here gets us some stuff for free. For example, we can immediately say that time of n squared is contained in time of n cubed, right? Why? Because n squared is O of n cubed. So another useful thing about big O is we don't have to argue about those because it's like, if it doesn't run in exactly n cubed time, fine. It's still in time of n cubed. So it allows some arguments to be made simpler, right? It's essentially, if you think about it, P here is just a polynomial time bound on the decidable languages, right? If you took LTM and you say, these are problems that are decidable at all, you just add this part here where it must take O of f of n steps, and suddenly you're in P, right? So it's just a polynomial time bounded version of the decidable languages, right? Question so far on P? Just the definition. Why is it a good definition? Why do we care about this class? LTM it's too simple for us to maybe not care because it's like studying this class is like studying the Turing machine. But now we're studying some special Turing machines or something, right? So it's like, what makes this interesting? So why is P a good class? Let me give you four reasons. One, if an algorithm has a polynomial time bound, we understand that it solves the problem that it knows something in a non-trivial way, right? Polynomial time, okay, so like we know that by the Church-Turing thesis, algorithms that are solvable correspond to having Turing machines that solve them. I claim a problem, the notion of efficiently solvable, which is an intuitive notion, corresponds to the formal notion of polynomial time in its runtime. So studying P is studying efficient algorithms. Studying LTM is just studying algorithms. Studying P is efficient algorithms. I need to argue with you that studying we have a very good philosophical reasoning about why does this notion of algorithm correspond with LTM. I need to make a similar argument about why does efficiency correspond to specifically polynomial runtime, and not maybe say linear runtime, quadratic runtime, right? Why specifically polynomial? Here's 4 reasons. 1, polynomial runtimes imply that you have some deeper understanding mathematically about a problem. For example, consider the path problem. You're given a graph G and 2 vertices S, T, and you're asked does there exist a path in G from S to T, right? This problem, is it in P or not in P?
It's in B.
Why?
You have an algorithm for it that's solved, that runs in polynomial time.
What's the algorithm?
A star, or
Yeah, like any of those, honestly, would work, right? So first off, the problem is solvable in exponential time, okay? Brute force search over all paths, check for all those possible paths, do any of them begin with S and end with T? That's an algorithm. It's a stupid algorithm. So we want a smart algorithm. Having a polynomial runtime implies you know something about the problem at a deeper mathematical level. And specifically, in the context of pathfinding in graphs, the deeper mathematics is basically like, if you take a path search is very local, in the sense that if you take a path and you cut it in half, you now have 2 paths. Every subpath in a path is also still a path, right? Graph search can be done in a very local manner where you just consider, at a vertex, you just only have to consider its neighbors. And then its neighbors' neighbors, and so on. It can proceed in such a very local way, right? And in fact, you could say it relies on a sentence like the shortest ST path is less than or equal to the shortest SUT path for all U. Dijkstra's, Bellman-Ford, Floyd-Warshall, basically they all rely on this kind of local property of graphs, right? It's less than the shortest path from S to U to T for any U. That kind of makes sense, right? That's why those algorithms work. And this is like an English characterization of like the main property of those algorithms when you prove their correctness. So you need some non-trivial understanding of the problem. Being in exponential time is not impressive. Being in polynomial time is. Okay. Number 2, closure. Polynomials are closed under things that are nice. For example, if f and g are polynomials, so are f plus g and f times g, right? If intuitively, efficient algorithms should be closed under certain operations, right? A combination of efficient algorithms should be efficient. So, an efficient combination, I should say. So for example, if you have 2 algorithms that have runtime O of f and O of g, what does f plus g correspond to? So let's say you have 2 algorithms with runtimes f and g. What algorithm has runtime f plus g?
running F and then running G.
Yeah. So running an efficient algorithm and then running a different efficient algorithm, that algorithm is efficient. Okay, fine. What algorithm corresponds to runtime of f times g?
Running F, but at every step of F you run G.
Exactly. For every step of one, if you have an efficient algorithm, and for each step of that efficient algorithm, you run an efficient algorithm, that's efficient. Okay? So like combining efficient algorithms efficiently should be an efficient algorithm. That sounds like it should be correct, the way we deal with algorithms. And it turns out polynomials behave like this. It's not true, for example, n squared, right? N squared times N squared is not N squared. So combining N squared algorithms does not give you an N squared algorithm. So there is a small problem with dealing with like low NP as your definition of efficient. Right. So combining efficient algorithms gives you an efficient algorithms. But let's say you have 10 algorithms, 9 of them are efficient, 1 of them is inefficient. 1 of them takes exponential time. No matter how you combine them, you should get an inefficient algorithm, right? So a single inefficient algorithm pollutes the combination in some sense, right? That's the point of closure. And there are other things that polynomials are closed under, of course, not just multiplication and addition, but composition and so on, right? So we get closure properties. That's good. 3. Okay. What is the largest runtime you've ever seen of an algorithm that is still technically polynomial? Open-ended question. You spend a lot of time on efficient algorithms, right? Making faster algorithms. I'm asking you, what is the slowest but still polynomial algorithm you've ever seen? Besides like 3, 4 loops, like that's a trivial one. But there are ones you may not remember from 3510, but they exist.
Are you asking for the specific algorithm?
No, I'm just asking like an open-ended question, like a poll of the audience. Have you seen any algorithm that runs in any time?
Into the 4, the slowest I've seen.
You saw an algorithm that runs in into the 4. What was the algorithm, if I can ask?
I can't remember.
Okay. Do you think it could be done faster, or were you convinced with n to the 4?
I was convinced. I didn't fully understand the algorithm at the time.
Okay. I mean, that's fine. Has anyone seen anything else? There's at least 2 cubic time algorithms in 3510. I don't know. Let's see if we remember them. Floyd-Warshall is cubic time, correct? It's in fact called the V3 algorithm because it's 3, 4 loops. It's V cubed time. And others? Bellman-Ford on a dense graph is another one. V times E when V is E squared. It's E cubed. Chain matrix multiplication, cubic time as well. The largest runtime of an algorithm I've seen is O of n to the 8. And this was for a problem called the Lenstra-Lovaz algorithm. It's not important what it does, but the 3 authors, Lenstra, and Lovaz, the 2 Lenstras are brothers, I don't know which one comes first, and then Lovaz, maybe you've heard his name, he's a combinatorics guy, big guy. They found an algorithm. This algorithm, it's not really important what it does. It finds a short orthonormal basis of a lattice. Okay, doesn't matter. But the important thing of this result, I think in the 80s, was that they solved the problem. It was the case that the fastest algorithms for this problem at the time were exponential time and above. So in fact, they were able to give a deeper mathematical understanding of the problem, and that was able to bring it into polynomial time. Now the problem is though, n to the 8 is really, really slow. They applied math to get it to polynomial, but it's not a good polynomial. That's okay, because it's hard to argue that a high degree polynomial is anything related to the notion of efficiency. We can prove, and we will in fact later on prove, there must exist algorithms that run in n to the 99 and cannot run any faster. Like there are algorithms we know that run at this level. You can in fact construct them by diagonalization. We'll be able to do so. We'll basically create a time of, we'll create an algorithm that runs in time n to the 100, which only diagonalizes over n to the 99 algorithms, right? It'll perform this diagonalization to ensure that it can't be decided any faster, something like this. We'll go through that proof. So there are problems that exist high in P that are definitely hard to solve. And in fact, this algorithm, I'll tell you, I implemented it, and I typed in it on my keyboard like 0, 0, 0, and then I hit enter, and the terminal hangs on a very short input because the algorithm is that slow. It's hard to say that this is an efficient runtime, but that's okay, because the author's contribution was bringing it within P at all. Once it can be brought in P, they bring not just the runtime, but a non-trivial mathematical understanding of the problem. then other people can advance the problem. You hand it off to engineers and other people like this. So then there's a sequence of papers, like 50 papers, things that are very specialized, and they break things down into the input cases, and they optimize the constants down. And there was like algorithms on like pruning and things like this, right? So they bring the problem, if a problem can be brought within P, and the problem is interesting, it can be brought low in P. And in a way that's also hard to measure the runtime. If you go to any number theory library and you ask for their version of LLL, it'll look nothing like the original paper because it's actually the sum of 1,000 papers that have improved upon and sped up the original LLL algorithm. When you take their implementation and you take any input, a gigabyte-sized input, and you hit enter, it solves it instantly. The speed is so quick you wouldn't notice the difference, right? There's no physical difference between it and constant time in some sense, but the important part was that this could only happen after Lenstra, and Lovász were able to bring it within P. Once they brought the math with that, other people can take over and do so, right? And in fact, I'll tell you, the algorithm you learn for chain matrix, for example, takes n cubed time, the dynamic programming algorithm. That's not the fastest algorithm for chain matrix. Other people have improved this to n log n. That algorithm is even worse. But know that, like, once you can solve the problem efficiently, somebody else can maybe solve it more efficiently. So it is the case that it appears that things that are high degree polynomials, boring, like they are contrived to exist there for no real reason. It appears, and this is a heuristic, it's not a very formal notion, all the interesting stuff is low in P, right? In fact, n to the fourth is the first time I've ever heard this. Students only mention n cubed. No one has ever told me they've seen an n to the fourth algorithm. N to the eighth is the largest I've seen. No one's ever seen like n to the 12th. And actually there's a poster hanging in Klaus that shows the algorithm improvement over time. And the first paper shows like n to the 23, and then the next paper shows n to the 4, right? So like it can always be brought to a low polynomial. Apparently, it appears that way. Right? Questions on that? Total heuristic on that, but thoughts? Okay. The fourth point is something called the extended Church-Turing thesis. The extended Church-Turing thesis is unlike the Church-Turing thesis because the Church-Turing thesis has a very grounded philosophical argument. The extended Church-Turing thesis basically says that all realistic models of computation, as in deterministic ones, can simulate each other with at most a polynomial overhead. So for example, we gave the fact that there was a runtime, one problem took a 2-tape machine linear time, but a 1-tape machine quadratic time, right? What this says is that all machines can simulate each other with overhead, but perhaps only a polynomial overhead. For example, the fastest realistic model here is probably the word RAM. So if a word RAM takes t steps, you can in fact you can simulate the word RAM on the 1-tape deterministic Turing machine in t to the 4th steps, which is a quartic. And that's a big overhead. You have a very slow model, can simulate a very fast model, but it can do so with a polynomial overhead. Not a good polynomial, but it's still a polynomial, right? And then I think like the 2-tape on the 1-tape simulation is n squared, 3 tapes on the 2-tape may be n log n, something like this, right? They're all simulations you can do on all of these, one from the other, that have overheads, but the overheads appear to be all polynomial. Now, why is this? There's not like a great philosophical reason for this. We just have evidence, right? There was one paper that was something like, tried to explore something like this, and it was not very successful, but it was like, what is a computer, like at the most general level? So they define a model of computation that uses pulleys, axles, gears, switch boxes, and levers, okay, and rope. Like, let this be the definition of a computer. Then they prove, like, okay, if this model of computation is governed by well-behaved differential equations, then, and if it solves an NP-complete problem using physics, it must have an exponential number of pieces. Like the number of parts required to do so is exponential. Something like this. So there are results like this that kind of like hint towards, okay, fine, like these are probably all polynomially related. The importance of that means, although there's a difference between the one tape and the two tape, it's only a polynomial difference. So every machine has the same P. So if you care about the runtime of an algorithm, that's different than caring about if there's a polynomial runtime of an algorithm. Because by caring about if there's a polynomial runtime, you don't have to care about it any further. If you only care about determining if there's a polynomial runtime or not, you can basically ignore machine things. You can just say, I don't care about the machine specific stuff. Just like sort this and then flip it. You can say that without having to argue about the machine's runtime of doing that because you only care about the polynomial. So although they have different runtimes, for example, time of n is different for which machine it is. Although they have different complexity classes, they have the same P. So P, in some sense, is machine independent. So although these runtimes are not good for us, like to measure algorithms, it's fine, just consider P. It's good, right? So these are 4 reasons that the class P is a good one. Nice class, pretty good. Questions on P? Yes?
So the definition P is equal to the union of all the time algorithms? Okay, and
The time of n to the k is the class of languages that there's a machine to decide that language such that the machine takes no more than n to the k steps. Questions?